So in this topic I will explain some of the basic concepts that we use when we talk about the optical instruments, microscopes and telescopes. These are the few terms: visual angle, power of accommodation, least distance of distinct vision and near point, magnifying power, resolving power of microscopes and telescopes. So these few terms will be used, and magnifying power, resolving power we will find out for microscopes and telescopes. Now let us first understand how do we see the objects. Light falls on the objects, it is reflected from the objects, then light rays reach our eye, and then image is formed on the retina. This is how. Let me say one object is here. This is a retina. On retina, the image is always inverted. It is the processing in the brain which makes it erect. This is eye lens. And this is the object. Let me say B. So, after passing through the eye lens, image is formed on the retina. This angle, we call it visual angle. So, visual angle is the angle subtended by the object at the eye lens. One ray, this one, another one can be taken this. This is the angle formed by this object at the eye lens. This is the visual angle. And this visual angle will decide what will be the size of the image formed on the retina. Size of any object, whenever we are looking at any object, our eye lens forms the image on retina, and the size of the image, this, will depend on the visual angle subtended by the object. So it is possible that the object is very large, but it is far away from our eyes, so it appears very small. You take this for example, if I take the same object, I mean same size here. Now if we find out the visual angle subtended by it, this one, let it be theta dash. So the size of the object is same, but when it is away from the lens, the size is smaller. The size of this image is smaller. So visual angle will decide the size of any object as perceived by our brain. We use microscopes and telescopes to increase the value of this angle. So they appear magnified. Okay, now power of accommodation, or see, in power of accommodation what we have to find out is what is the distance of image from the lens. In this particular case, this is eye lens and here is the retina. So actually the value of V is fixed. If you can recall the expression 1 by F is equal to 1 by B minus 1 by U. So the value of V is fixed. The distance between retina and eye lens is constant for our eyes. So depending on the distance of the object from the eye lens, F will change. So the muscles of the eyes, they have this capacity to change the curvature of the two surfaces. As a result, the focal length changes. Focal length depends on the radii of curvatures. So focal length of the eye lens keeps on changing. It varies when the object is far away, or we say eye is focused at infinity. Then focal length is maximum or power of the eye lens is minimum. So when we are looking far away objects at infinite, power is minimum, F is maximum, and power is minimum for infinity. Now as the object is brought closer, so the power keeps on increasing or focal length keeps on decreasing, and the size will also increase. So this ability of the eye lens to change its focal length or power is called the power of accommodation. Eye has this tendency, has this ability to change the focal length or the power of the eye lens. So this ability of eye, we call it power of accommodation. But it doesn't mean that no matter how close the object is brought, the eye will be able to see it clearly. There is a limit to it. Near point is that point up to which we can see the objects clearly. Means if I bring the objects closer, suppose this is near point. If I take it as near point, it means I can see the image of this object from infinity up to this point only. If I bring it closer than this, image will be blurred. For a normal eye, this distance is 25 centimeter. So 25 centimeter, this distance. Distance is called least distance of distinct vision. It means the minimum distance from the eye lens up to which an object can be seen clearly. So least distance of distinct vision. And this point, this position, that is called near point. The distance, least distance of distinct vision. For normal eye, this is 25 centimeter. If this changes, if the near point is say 30 centimeter, or if the near point is say 20 centimeter, then the eye is not normal. This is called eye defects. It may be myopia, it may be hypermetropia. That's different topic. Okay, so when the object is at infinity, power is minimum. When the object is at this point, power is maximum. This distance is least distance of distinct vision and its value is 25 centimeters for normal eye. Magnifying power is the ability of an instrument to magnify. See, this is for a microscope. So this is the maximum size of an object that we can see even without using any instrument. This is the height of the object and this is the visual angle subtended by the object. Now if I use any instrument and this image is magnified, then the size of the image upon size of the object. This we have done for lenses. This is how we define magnification, size of image upon size of object. Now, where should the object be placed? Where can the image be set? That we will take specifically for telescope and microscope separately. But height, size of image upon size of object, or we can also say the visual angle subtended by the image and the visual angle subtended by the object. This ratio is called the magnifying power of any instrument. Resolving power is different from magnifying power. Magnifying power is just the ability of a lens to magnify. Magnify means an object which is visible to the naked eye has certain size, say this much. When we are looking using the instrument, this appears bigger. Then we can say the instrument is magnifying it. Resolving power is something different. It is not the magnification. It is not increase in the size of the object as visible to the human eye. It is something. Now I am showing you an activity. Now as I move my camera closer to this paper, now see, it is a set of two lines. So we can say from this distance these lines are resolved but from this distance we are unable to see them as two distinct lines. There are two objects which are very close, but you cannot see them separately. I have shown in this activity that there are two lines, but when you see them it appears one. So if we use an instrument, optical instrument, and those two lines are visible to you separately, then we will say that the instrument has high resolving power. So resolving power is actually the ability of an instrument to produce distinct images of closely spaced objects which are otherwise not visible to our eyes. I mean, there are many things. In this example, I have shown you two lines drawn very close. Otherwise, it may also happen that there are some stars, binary stars, means two stars very close, but to our eye, it appears just one. So it's possible. So resolving power is ability of an instrument to produce distinct images of two objects which are otherwise very close. Now for microscope and for telescope we define it slightly differently. For a microscope, I take now two objects which are very close, and we are using a microscope to see these objects. This is the objective of the microscope. I have drawn this. So this is the focal length. Now the rays become parallel. If the two objects are visible distinctly using this microscope, then this distance we call it limit of resolution. The minimum distance between the two objects which are visible distinctly. It means if the distance between the two objects is less than the limit of resolution, we cannot see them separate. Okay, so minimum distance. If the distance is more than the limit of resolution, we can see them separately. So minimum distance between the two, that is called limit of resolution. And resolving power is the reciprocal of limit of resolution. Or if I use d for it, so it is 1 by d. And this d is lambda upon 2 mu sine theta. The derivation of this expression is beyond your syllabus. It requires some mathematics at higher level. It involves a diffraction actually also. So you can leave that. Distance between the two objects which are visible distinctly. This is lambda upon 2 mu sine theta. Lambda is the wavelength of the light that we are using. Mu is the refractive index of the medium, this one, between the objects and the objective. And theta, we call it half of the cone angle. The cone is subtended, half of this angle is called theta. This quantity, mu sine theta, we also call it numerical aperture. Numerical aperture. So what is resolving power now? resolving power is 2 mu sine theta by lambda. So if we want to increase the resolving power of a microscope, we can change mu. So it means even if we keep water between the objects and the lens, resolving power will be increased. We can change the wavelength for a smaller wavelength, means for violet. For violet, the resolving power is more than for red. Same way, even the size of the lens will make a difference in the resolving power. If I use bigger lens, theta will be increased, so resolving power will also increase. Okay, now for telescope. For a telescope also, the resolving power is reciprocal of limit of resolution. But limit of resolution is defined slightly differently. Here it is defined in terms of the angle, not distance. Theta is the angle subtended by the two objects. A and B are two objects which are very close. Theta, the minimum angle subtended by the two objects at the objective when they are just resolved. This is called the limit of resolution. So A and B are two objects which are very close, maybe binary star. Okay. So one star this, one star this. And when the telescope can see two distinct images of these two stars, then whatever angle is subtended, that is called the limit of resolution. Resolving power is 1 by theta. So smaller is the value of theta. It means the instrument can see them separately even if they are very close. That's the meaning of theta is small. And resolving power will be higher in this case. And theta is 1.22 lambda by d. So resolving power can be written as d upon 1.22 lambda. Here, lambda is the wavelength of the light coming from the objects to the objective, and d is the diameter of the objective lens. So resolving power of a telescope will depend on the diameter of the objective lens and the wavelength of light. So this is resolving power of telescope. So I'm revising again all the important points. Resolving power is the ability of any instrument to produce distinct images of closely spaced objects. For a microscope, limit of resolution is the minimum distance between the two objects just resolved by the microscope. And for a telescope, the limit of resolution is the minimum angle subtended by the objects when they are just resolved. For a telescope, resolving power is d upon 1.22 lambda, so it is depending on the diameter, it is depending on the wavelength of light. And for a microscope, resolving power was 2 mu sine theta by lambda. Lambda is the wavelength of light and mu is the refractive index of the medium between the objects and the objective, and theta was half of the cone angle. So it's all from this topic, and we shall be using all these terms when I will take telescope and microscope separately. Goodbye.